So the next statistical measure we're going to look at is variance. So we're looking at our discrete random variable. Here's the formula for variance. So it's very similar to the expected value one, but you'll notice instead of x times the probability of x, it's x minus mu, which represents the average or the mean, squared. Px is still the probability. U is the expected value that we talked about yesterday. So this x minus mu part, what is it? Well, it's what we call the deviation from the mean. How far away from the average is our actual piece of data? And this one's a measure of spread then, because it's basically measuring how far away from the average are we. Let's go back to our milk survey. So same survey, and that's where we got to yesterday. So we had xpx, and then we created a new column xpx, and we found that the expected value, or the average, ended up being the sum of xpx. So that's pretty much where our table's up to at this stage. I'm now going to add in this x minus mu squared column. Boy, this is what you have to do. X minus the average, so minus 2.2, but then squaring it. So for each one of those, that's what I've done there. We want to then find that times the probability. So I then get that row and multiply it by the probability. And then the sum of that row, which is 1.52, is the variance. And can I be honest with you? If you do it that way, you're crazy. A little bit of playing with the figures creates an easier way of doing this. So we're saying it's the sum of x minus mu squared times px. But yesterday we defined expected value to be something times the probability of x. So that actually is the expected value of x minus the average squared. Now I just play around with some of those properties of expected values. If I was to expand out x minus mu squared, I'll get x squared minus 2 mu x plus u squared. And we said that the expected value of several things added together is the same as just finding the expected value of each individual bit and add them together. Well, working from the back, mu squared is a constant number. That's whatever the average is squared. And the expected value of a constant is that constant. So that's mu squared. The middle term, 2 mu is a constant, and we saw that we could factorise out the constant. So that's going to be 2 mu times the expected value of x, and the first part is just the expected value of x squared. But hang on, we said the expected value of x is mu. So in fact that middle term is now 2 mu times mu, 2 mu squared, and I end up with this. The variance of x is the expected value of x squared minus mu squared. And that is the one to use, because expected value of x squared will just become x squared times px. So let's go back to our table. That's where we were at the end of yesterday. That's the table we had created. All it means now is I just need one more row. So yes, we found that mu was 2.2. So my next row is x squared px. Now I don't know about you, but to me that is much more logical to remember if you look at how the rows go down. I got px, I got xpx, I got x squared px. So each time I'm just multiplying the row above by x. As I say, to me logically that's easier to remember. Now 6.36 is the sum of that row. That's not going to be our answer, because we said the variation will be the expected value of x squared, which is the sum of that row, but then minus the answer that we found for the average squared. Okay, so that 6.36 is not our answer. That's the expected value of x squared. To find the variance then, I'll go, okay, it's that answer that I just found, 6.36, minus the answer we found for the average squared. And what do you know? It's 1.52. So I say, the first way of doing it is the formal. It's a bit like, last year when you looked at standard deviation and you had the square root of x minus mu squared and all that sort of stuff. But logically, this is a much easier way of doing it. Which brings us to that thing of standard deviation. What is that then? How does that come into play? If you think about what we just found, the variance and the units of that, because we're squaring the expected value. and it was the deviation squared. So whatever the units are, this variance is going to be measured in those units squared. Now, if I want to use it for comparison, I want things in the same units. I don't want them in units squared. So how do I change from units squared to units? You find the square root. And so that's all the standard deviation is. I then just find the square root of that. And that becomes standard deviation. Or another way of thinking about that is sigma squared is variance. So sigma is standard deviation. Sigma squared is variance. So for our example then, if we wanted to find the standard deviation, it'd be the square root of 1.52, so about 1.23. I'm going to talk to you a bit about standardising data. Do not panic too much about it, right? But I want to show you, talk about Z-scores and where it all comes from. So what data standardisation is it allows us to compare data sets. Yeah? How did you go in English versus how did you go in maths versus how did you go in chemistry versus how did you go in physics? But they're all different tests and have different averages and things like that. So we want a way of comparing data sets. So our original data would have an expected value. It would have a variance. So what you find, some subjects, not maths, do this. Have you ever had this happen where you've had a subject and they said, oh, we're not happy with these marks, so we're going to, and they sometimes throw around the word scale. They sometimes use that word, but their idea of scale is not what scaling is. And they just simply go, you know what, we're just going to add 10 to every mark. Have you ever had that happen? Right? Well, let's see what that does with the data. So here's how we're going to do it. This is not standardising, by the way. But say we're just going to add a constant amount to each piece of data. So I now have this new random variable y. So whatever we scored for x, plus some constant amount. Then I add that to every piece of data. So the expected value of y becomes the expected value of x plus a constant. But we said we can deal with those separately. We know the expected value of x is mu, and expected value of a constant would be the constant. So we have lifted the average up by the constant, in effect. Okay, but what happens to the spread of data? The variance of x plus a constant. That's what I say. Just trust me on this one. Don't panic, you're not going to be asked to have to prove this or anything like that. But by our new formula, it's going to be the expected value of x plus c squared minus the new average squared, which was mu plus c. Okay, expanding all this out. Now with the expected value on the left hand side, expected value of x squared is that. Expected value of 2cx, I can factorise out the 2c and I get 2c times the expected value of x. Expected value of c squared will be c squared. But expected value of x is mu, so that becomes 2c mu. Playing around with all that, I end up with the expected value of x squared minus mu squared. Hang on, that was the variation of x. We've done nothing to the spread of the data. All we've simply done is added the same amount. It does not change the spread at all. So simply adding a constant doesn't change the shape of the data at all. It just shifts it. It's like shifting a curve. It's like saying, there's the original data. If I was to draw a picture of it, all we've done is gone, whoop. Can you see a problem with that? You know, think of an obvious problem. The obvious problem is this. Just say in that original set of data, the red data, someone scored 100%. What's going to happen? 110%. Wait, you can't get 110%. So what do they end up doing? They still keep them on 100. So it's not fair. It's not fair. So that's why you simply can't just add the same amount to every score. All right. What about if they said, okay, we're just going to divide it by a constant amount. Let's see what that does to the data. So the expected value of x divided by k and the variance of x divided by k. How is this going to change? Well, over in expected values, again, expected value of k is a constant, so it just stays as k. Our average will be divided by whatever the constant is. But what happens with variance when we play around with this one? We end up with, okay, let's go through it. Expected value of k squared would be k squared And then on the top, we end up with the variance over k squared. So we get sigma squared on k squared, which is sigma on k squared. So what has happened? Yes, we have changed the shape of the data, because there's definitely a change to the variance there. It's no longer sigma squared, it's now sigma squared divided by k squared. So as a picture, there's the red data with the average is mu. Now, depending on what that constant is, I've assumed the constant is going to make mu on k a smaller number. So the average gets moved over, but the data gets pushed together because the variance will become a smaller number. That brings me to z-scores. And so what we actually do with z-scores is sort of combine that idea. So normalise the data. There's the formula. Z's going to be x minus the original average, and we'll divide it by the original standard deviation. And if we do that every time, this is what happens. So z is my new random variable. Play around with the expected values, using the same idea. Expected value of a constant will be a constant. And I end up with 0 for the average. Average always comes out to be 0. Now with the variance, playing around with this one, we end up with 1. So every single time, if you do that, you end up with an average of 0 and a deviation of 1, and that's where you get your z-score from. Remember I said z-score is how many deviations from the mean, because in this 1 represents 1 deviation, and so on. And it allows you then to compare different sets of data. So the average of the z will be 0, the standard deviation will be 1. 13C, say, don't panic too much about that last bit. That's showing you that how we can use these stats to, well, some people say manipulate the data into something more useful.